the summer of 1950. You're at Los Alamos National Laboratory.
Hallowed ground. I mean, this is where the modern world was basically invented, for better or worse.
Exactly, and you've got the greatest minds of the century all around you. But we're not in a lab, we're on a walk to lunch.
Right, just a casual stroll over to the Fuller Lodge. And the group is, well, it's a who's who. Enrico Fermi, Edward Teller, Herbert York, Emil Konopinski.
Titans, absolute titans of physics, and they're not talking about quantum mechanics or fusion. The conversation starts with a joke.
A cartoon, of all things, from the New Yorker.
And the cartoon was just, it was silly. It showed these little green aliens getting out of their flying saucer and stealing municipal trash cans.
The most mundane invasion imaginable. And that gets them talking, joking about it. How fast would a flying saucer have to be? Is faster than light travel even a thing? It's just banter.
Just banter. But one of them goes quiet. Enrico Fermi.
And you have to understand who Fermi was. They called him the Pope of Physics because his pronouncements felt infallible. He had this almost scary ability to do complex calculations in his head.
Ballpark estimates that were more accurate than most people's detailed work.
Exactly. He could estimate anything. The number of piano tuners in Chicago, the yield of an atomic bomb, just by watching the flash. So as the others are laughing, he's just calculating.
He's running the numbers. The age of the galaxy, the number of sun-like stars, the probability that life arises, the time it would take for a civilization to spread.
He's running all of it through that incredible mind of his while they're sitting down to eat. And then he just stops, looks up at his friends, and he asks this simple four-word question.
Where is everybody?
And that question just hangs in the air.
Yeah.
Because it wasn't philosophy, it was a conclusion. It was the result of a calculation.
He was saying that, given the numbers, the evidence of other technological civilizations should be overwhelming. Obvious. They should be here.
The fact that they aren't. The fact that we look out and see nothing. That's the paradox. It's this enormous contradiction between a statistical expectation of a crowded, noisy universe and the empirical reality of what we call the Great Silence.
And that's what we need to unpack. Why the expectation is so high and why the silence is so disturbing.
To really feel the weight of Fermi's question, you have to appreciate the pillars that his calculation stood on. And it all starts with this idea that we're not special.
The principle of mediocrity, which sounds insulting, but it's a core scientific assumption.
It is. It assumes that Earth is a pretty standard rocky planet, orbiting a pretty standard star, in a pretty standard part of a pretty standard galaxy. If you accept that, then the numbers just explode.
Let's start with the big one, time. The universe itself is what, about 13.8 billion years old?
Yeah, the Planck data from 2018 really nailed that down. 13.8 billion years. And our galaxy, the Milky Way, isn't that much younger. It's been forming stars for maybe 13 billion of those years.
So there's been this immense, almost incomprehensible stretch of time for things to happen. This isn't a rush job.
Not at all. We're talking about enough time for stars to be born, live their entire lives, and die, seeding the next generation with heavier elements.
Yeah.
Enough time for that cycle to repeat over and over and over.
Long before our solar system even existed.
Billions of years before, which means there were billions of years for life to arise, evolve, build civilizations, and, well, do whatever it is that civilizations do.
Okay, so that's the timeline. What about the real estate? The sheer number of places where this could happen.
It's just as staggering. The Gaia mission data gives us a pretty solid inventory. We're looking at somewhere between 100 and 400 billion stars in the Milky Way alone.
100 to 400 billion.
And a total mass of about 1.5 trillion suns. The scale is just, it's mind-bending. Even if the chances of a technological civilization are tiny, 1 in a million, say.
You'd still end up with hundreds of thousands of them in our galaxy.
At least. The numbers are just overwhelmingly in favor of life.
Yeah.
And then there's the chemistry.
Right. It's not like life is made of some incredibly rare exotic element.
No, not at all. That's maybe the most compelling pillar. You look at what the universe is made of. After hydrogen and helium, the stuff made in the Big Bang, what's most common?
Carbon, oxygen, nitrogen.
The very building blocks of every living thing we've ever seen. The ingredients for life aren't a special order, they're a cosmic standard. They were abundant in star systems that formed 10, 11 billion years ago.
So you've got the time, you've got the real estate, and you've got the raw materials everywhere you look.
Which brings us back to what Fermi was really focused on. It wasn't just the distance between stars, it was the time, the head start factor.
Because our sun is a relative latecomer to the party, right? It's only 4.6 billion years old.
A total newcomer. The peak of planet formation in this galaxy happened billions of years before Earth was even a cloud of dust. You could have had Stable, rocky planets forming 7, maybe 8 billion years before us.
Think about what that gap actually means. A 7 billion year head start. We've gone from the first steam engines to artificial intelligence in less than 300 years. The gap between us now and our ancestors using stone tools is under 3 million years.
In a billion years, it's an eternity. If a civilization got a 1 billion year head start on us, their technology wouldn't just be advanced, it would be indistinguishable from the laws of nature itself. It would be magic.
They would have solved every problem we can conceive of and a million more we can't. Interstellar travel would be trivial.
It would be ancient history to them. They'd have had time to re-engineer star systems, build structures on a galactic scale.
And this isn't just a thought experiment. We can point to actual stars. There's an exoplanet, Kepler 452. It's often called Earth's older cousin.
It is. It's in the habitable zone of a star, very much like our own. But the key is, its star is 6 billion years old.
So 1.5 billion years older than our sun.
1.5 billion years. That's the head start. If life followed a similar path there, they should have been technological when the most complex life on Earth was just algae.
They would have had time to colonize the entire galaxy, not just once, but hundreds of times over, before humans even existed.
So the expectation, based on all of this, is just relentless. The galaxy should be old, it should be industrialized, it should be noisy, a mature, settled place.
And instead, what we get is the silence, an absolute profound silence.
So, for a long time, we've tried to organize our thinking on this with something like the Drake equation.
Right, which isn't really an equation to get a firm answer, but more a way to structure the problem, to organize our ignorance, as they say.
Exactly. It breaks it down into factors: the rate of star formation, the fraction of those with planets, the number of habitable planets per system, and so on.
And the incredible thing over the last couple of decades is that we've actually started putting hard numbers to the first few terms. They're not just guesses anymore.
Not at all. The Kepler Space Telescope, that was a revolution. It basically confirmed that the number of stars with planets is, well, pretty much all of them. Planets are standard equipment.
And the initial data from Kepler was just wildly optimistic, wasn't it? It suggested something like 22% of sun-like stars had an Earth-sized planet in the habitable zone.
It did, and that led to these incredible headlines. Tens of billions of Earths in the Milky Way. It made the paradox even worse. If there were billions of potential homes, where was everybody? But
the newer data, especially from the TESS satellite, has, well, it's thrown some cold water on that optimism.
To put it mildly, TESS is looking at the whole sky, and it's giving us a much more refined and, frankly, more pessimistic picture. And it's all because of something called the radius valley.
Okay, what is that? A valley in the data?
It is. When you plot the sizes of all the thousands of planets TESS has found, you see this strange gap. There are lots of planets smaller than 1.5 times Earth's radius, and lots of planets bigger than 2 times Earth's radius, but very few in between. There's a valley.
And why is that important? What does it tell us?
It suggests that there are 2 very distinct types of common planets. The ones on the small side are likely true rocky super-Earths. But the ones on the other side of the valley, even if they're only twice Earth's size, are probably mini-Neptunes.
Meaning they have these huge, thick, crushing atmospheres of hydrogen and helium, not somewhere you could stand on a surface.
Not at all. Or they might be the boiled-off cores of those planets, stripped of their atmospheres by their star. Either way, they are completely unsuitable for the kind of life that could develop technology.
So a lot of what we thought were Earth-like candidates are actually in these traps.
Exactly. And this leads us to the really crucial updates from the last couple of years, around 2025. These new studies are arguing that habitable zone is a dangerously simple concept. Just having liquid water isn't nearly enough.
You need a true Earth-like habitat.
That's the term, yeah. And the list of requirements is getting longer and much, much stricter.
Okay, so what's on that list, beyond just having water?
Well, first, you need the right kind of atmosphere. One dominated by nitrogen and oxygen like ours, not a thick, toxic blanket of CO2 like on Venus. You also need really effective long-term ways for the planet to regulate that CO2.
A planetary thermostat, basically, plate tectonics and so on.
Precisely. But the biggest one, the real killer for a lot of planets, is the need for a strong global magnetic field.
To protect the atmosphere from being stripped away by a star's solar wind?
It's non-negotiable for long-term survival. Without that magnetic shield, especially around the more common and volatile red dwarf stars, your atmosphere gets sandblasted away over a few billion years. Any water boils off, become Mars.
A dead rock. So even if you start in the perfect spot, if your planet's core cools too quickly and that magnetic dynamo shuts down, it's game over.
It's game over. And when you apply all of these strict filters, the right size, the right atmosphere, a persistent magnetic field, the numbers just plummet.
So we go from billions of potential Earths down to...
The 2025 estimates, like from the Lammer studies, suggest the number of true Earth-like habitats in the entire galaxy might only be around 100,000. Maybe a few 100,000 at best.
100,000. I mean, that is a 99.999% reduction from where we started.
It's a colossal drop. It makes the rare Earth hypothesis, the idea that our setup here is incredibly unusual, look a lot more plausible.
It definitely softens the paradox, but it doesn't solve it, does it?
No, because 100,000 is still a huge number. 100,000 chances over 13 billion years for not one of them to produce a civilization that made it out. That's still statistically baffling.
It's the difference between looking for a needle in a continent-sized haystack and looking for one in a city-sized one. The search is smaller, but it's still incredible that we've found nothing. Absolutely nothing.
So we have to pivot from the expectation to the hard reality. And that reality is best summed up by what the physicist Michael Hart called Fact A.
And Fact A is just brutally simple.
It's the most straightforward empirical observation you can make. There are no intelligent beings from outer space on Earth now. No ships in orbit, no alien artifacts in museums, no probes mining our asteroid belt.
And it's not for lack of looking. I mean, we've been actively searching for decades.
Ever since Frank Drake pointed a radio telescope at a couple of nearby stars back in 1960 with Project Ozma.
And all he heard was a secret military experiment.
Right, a false alarm. But compare that to now. Today we have Breakthrough Listen. It's not a small side project. It's a $100 million industrial scale search.
Using the biggest telescopes on the planet, Green Bank, Meerkat in South Africa.
And the really big change in the last couple of years has been the processing power. They're using massive AI systems to sift through the data to filter out all our own radio noise. It's accelerated the search by something like 600-fold.
So we're listening deeper, wider, and smarter than ever before. We're targeting those specific planets found by tests, yes. And after all that, petabytes of data. What's the result?
The result is the same. An unbroken, profound silence. Zero. Not a single confirmed technosignature.
So if they're not talking, maybe they're building. That's the other way to look, right? For giant engineering projects.
Megastructures.
Yeah.
Specifically, Dyson spheres.
The idea that any really advanced civilization would eventually need all the energy from its star and would build a structure to capture it.
And the beauty of this is that it doesn't depend on alien psychology. It depends on thermodynamics. You can't use that much energy without producing waste heat.
So the sphere would block the visible light from the star, but it would glow brightly in infrared. A very specific signature.
An unmistakable one. And for a moment there, in 2024, it looked like we'd found it. There was huge excitement.
I remember that. 7 potential candidates were identified. It was all over the news. This was it.
The data looked good. It really did. But the follow-up studies came in pretty quickly by early 2025. And, well, the prosaic explanation won out again.
What were they?
They were something called hot dust-obscured galaxies. Or hot dogs, for short.
Hot dogs. So, distant galaxies masquerading as alien megastructures. How does that work?
You have a very active, very powerful galaxy billions of light years away. It's shrouded in a massive cloud of its own dust. The dust absorbs the intense light from the galaxy's core and re-radiates it as heat, as infrared light.
And because it's so far away, it just looks like a single point of light, like a star that's giving off way too much heat.
Exactly. It perfectly mimics the signature of a Dyson sphere. So it wasn't alien engineering, it was just dust. Very hot, very distant dust.
Another dead end. The silence holds.
But there's one more piece of evidence for the silence, and it's maybe the most profound of all. It comes from the New Horizons spacecraft.
The probe that flew past Pluto, it's way out there now, in the Kuiper Belt.
Deep space, far from the sun's glare, far from the dust in the inner solar system. And from there, it took a measurement of the total background light of the universe, the cosmic optical background.
Basically, how dark is deep space, really?
Yes. And the finding was that it's much, much darker than our models predicted.
Why is that significant? Why does a darker universe point to silence?
Because if the galaxy were full of Type 2 civilizations, all harnessing their stars, there would be light leakage. Think of Earth at night from space. You see the cities. Now imagine billions of industrialized star systems.
There would be a background glow, a kind of cosmic light pollution.
An ambient, diffuse glow from all that technology. The fact that the sky is so dark puts a hard thermodynamic limit on how much activity is going on out there. The darkness itself is a measurement of sterility.
So it's not just that they're not here or not talking to us, it's that they're not even turning on the lights anywhere we can see.
The silence is measured. It's in the radio, it's in the infrared, and it's in the darkness between the stars.
And when you take that proven silence and you combine it with the immense timescale of the galaxy, you get to a very, very bleak conclusion.
You get to the Hart-Tipler conjecture. This is where the argument becomes really rigorous and, frankly, really depressing.
Michael Hart in 75, Frank Tipler in 80. They basically said, let's start wondering if they can travel between the stars and just calculate how long it would take them to spread.
And their argument flips the whole thing on its head. It says the absence of evidence is evidence of absence, because if they existed, they would already be here.
And this all comes down to the colonization timescale. They made some very conservative assumptions. Let's say their ships travel at just 1/10 of 1% of the speed of light.
So 0.0001 c. Slower than some of our own probes. Very, very slow by cosmic standards.
And the model isn't one empire sending out ships everywhere. It's simpler. A ship arrives at a new star system. It takes its time, maybe a few thousand years, to build up its own industrial base. And then what does it do?
It sends out its own ships to the next set of stars.
So it's a self-propagating wave. It grows exponentially, like a slow-motion fire spreading through a forest.
And Hart ran the numbers on this. Even with those incredibly slow speeds and long pauses between waves, the time it would take for that colonization wavefront to cross the entire Milky Way from one side to the other.
It's shockingly fast.
It's between 650,000 and 2 million years.
2 million years. Let's sit with that number. The galaxy is 13 billion years old.
Right. 2 million years is nothing. It is 0.015% of the age of the galaxy. It's a rounding error.
2 million years ago on Earth, our ancestors, Homo erectus, were just figuring out how to make stone axes. That's the timescale we're talking about.
So if any civilization, anywhere, had developed this capability, like just, say, 50 million years ago, a tiny fraction of the galaxy's life, they would have had time to cross the galaxy 25 times over.
They would have saturated every habitable system. Our solar system would have been surveyed, cataloged, and probably colonized millions of years ago.
The fact that we are here on an uncolonized planet in an asteroid belt that is not being actively mined by anyone is, to Hart and Tipler, mathematical proof they don't exist.
And Tipler took it one brutal step further, right? He removed biology from the equation entirely.
He did. He said, why would you send fragile, slow-reproducing biological beings? You'd send machines, self-replicating spacecraft, von Neumann probes.
The ultimate unstoppable machine.
You design a probe with one directive. Go to a new system, find raw materials in an asteroid belt or on a moon, use those materials to build perfect copies of yourself, and then launch those copies at the next stars.
It's viral. It's pure exponential growth. You only have to build one and it does the rest of the work for you.
And its spread would be relentless. If even one civilization launched these things a billion years ago, our solar system should be teeming with them right now. The fact that it isn't, for Tipler, was the final nail in the coffin.
But there's a counter-argument to that, isn't there? A way out from that ironclad logic.
There is one major rebuttal, and it's a compelling one. It's called the error catastrophe.
Digital cancer.
That's a great way to put it. Think about it. Any kind of replication, whether it's DNA or a machine's digital blueprint, is subject to copying errors, mutations.
And over millions of years and millions of replication cycles.
Those errors would accumulate. Without perfect error correction, the probe's core instructions, its DNA, would degrade.
So they would start building faulty copies, or copies that have forgotten their original mission.
Exactly. They might just turn into inert space junk, or they might become something else entirely, something that just consumes local resources but has lost the imperative to expand. The viral spread would fizzle out.
So the galaxy could be full of the dead, mutated husks of these failed probe fleets.
It's possible, and it lets you have ancient alien civilizations without them violating Fact A. But it's still a solution that results in a silent, empty-looking galaxy for us. The end result is the same.
Right, whether they never launched or their launch just failed over time, we're still alone.
Which forces us to confront this final, huge idea, Robin Hansen's concept of the Great Filter.
The idea that if the starting point is simple chemistry and the end point is a galaxy-spanning civilization, but we see no one at the end point, there must be a wall somewhere in between.
A colossal, almost insurmountable barrier that stops virtually all life from making it through.
But before we get to what that filter might be, we should probably look at the arguments that maybe the colonization model itself is just wrong. Maybe expansion isn't inevitable.
That's a fair point. Carl Sagan, for one, argued against the uniform wavefront idea. He proposed something based on percolation theory.
Like water seeping through porous rock.
Precisely. Colonization might not be a solid wave. It might be a patchy, slow diffusion. Some colonies succeed, others fail. Some just lose interest in expanding further.
So the galaxy might be settled in these isolated clusters with huge, uncolonized voids between them.
And we, just by random chance, happen to be in one of those voids. We're not alone. We're just in the cosmic suburbs. It's a possibility.
Okay, what's another one? Another reason they might not expand.
The ocean world trap. This one's become more popular with the new exoplanet data. We think a lot of these super-Earths might be water worlds, covered in oceans hundreds of kilometers deep.
So you could have intelligent life evolve there, something like a hyper-intelligent octopus or whale.
Absolutely. But they are permanently trapped.
How so?
No fire. Without dry land, you can never discover fire. Without fire, you never get metallurgy. No metal tools, no electricity, no chemistry, and certainly no rockets. They could be brilliant philosophers, but they can never leave their planet.
A planetary scale prison, that's a pretty effective filter.
And then there's the sustainability argument. This one looks at the psychology of expansion itself. The kind of civilization that wants to colonize a galaxy in 2 million years is probably hyper-aggressive and consumes resources at an insane rate.
And that kind of behavior might be inherently self-destructive.
It might be. They could burn through their own planet's resources and collapse long before their colonization project gets very far. So there could be a selection bias in the cosmos.
The only civilizations that survive for billions of years are the quiet ones. The ones that achieve sustainability and choose not to expand.
The silence, in that view, isn't the sound of absence. It's the sound of wisdom, of civilizations that conquered their self-destructive urges. They're out there, but they're deliberately quiet.
But even with all these potential off-ramps, the core question of the filter remains. It presents us with this stark, existential choice.
Is the filter behind us, or is it in front of us?
Let's take the good news first. The possibility that the great filter is in our past.
This is the hopeful view. It means that one of the steps we've already taken was the near impossible one, that we have, against all odds, won the cosmic lottery.
And what could that step be? The jump from non-life to life in the first place, abiogenesis.
That's a leading candidate. Or maybe the jump from simple prokaryotic cells to complex eukaryotic cells. Something that seems common to us because it happened here, but is in fact monstrously improbable.
The fact that we're here having this conversation is proof that we passed the test. The silence of the universe is just confirmation of how special we are.
And this view is definitely bolstered by that new data we talked about, the reduction in true Earth-like habitats. It makes our specific circumstances look even more rare, even more precious. In this scenario, the silence is a good thing.
But then, there's the other option, the terrifying one.
The terrifying one. The filter is in our future.
This means that life is common, intelligence is common, technology is common, but something always, inevitably, goes wrong.
Something happens to every technological civilization that prevents it from reaching the interstellar stage, a universal self-destruct mechanism.
So the universe isn't a cradle, it's a graveyard. And the silence is the sound of all those failed civilizations.
We aren't the first. We're just the latest in a long line of species who reached this exact point, right before the end.
What could that future filter possibly be? I mean, the original fear at Los Alamos was obvious.
Nuclear war. The moment a species discovers the power of the atom, it gains the ability to destroy itself in an afternoon. That's a very potent filter.
But the list of potential culprits has grown since then.
Oh, absolutely. Planetary scale ecological collapse from resource depletion or climate change. A genetically engineered pandemic that gets out of control.
But the one that seems to dominate the conversation now is technology itself. Artificial intelligence.
A superintelligence. One that we create but can't control. An ASI that is so powerful, but its goals aren't perfectly aligned with ours. It might not be malicious, it might just see us as an obstacle to achieving its goal more efficiently.
And it would remove that obstacle.
Yeah.
Us.
The great filter, then, is that incredibly brief, volatile window between inventing radio and achieving a stable, multiplanetary existence. And the silence of the universe is the evidence that, so far, nobody has ever successfully made it across.
So we've laid it all out. The scale and the chemistry say the universe should be full. The sheer amount of time says it should be ancient and settled. Hart-Tipler logic says they should be here.
And yet, breakthrough listen hears nothing. Our telescopes see no megastructures. The darkness of deep space tells us no one is using vast amounts of energy. The paradox isn't just a puzzle anymore. It's a conclusion backed up by mountains of null data.
It really forces you to look inward, doesn't it? The search for aliens has become a search for our own future, our own chances of survival.
It has. Every failed search, every time we find dust instead of a Dyson sphere, it just raises the stakes. It makes the two possibilities sharper.
If Hart and Tipler were right, if we genuinely are the first, if we are alone, then the weight of that is just crushing.
The entire responsibility for consciousness in this galaxy, for meaning, for art, for science, it all rests on our very fragile shoulders. There's no one older or wiser coming to help.
And the alternative is somehow even worse.
That the silence is the sound of the filter that awaits us, that failure is the default state of civilizations like ours. And if that's true, then figuring out exactly what that filter is, that's not an academic question.
It becomes the only mission that matters, the singular obsession for our entire species. Because the question isn't the one Fermi asked at lunch anymore. It's not, where are they?
The question the data forces us to ask is much simpler and much more terrifying. It's, will we last?